We're going to talk today about intermolecular forces. We had talked about chemical bonding. Chemical bonding is considered intra. So we had talked about chemical bonds, but chemical bonds are inside, right? Inside the molecular, intramolecular forces. So intermolecular, it's going to be the forces between molecule and molecule. So intermolecular forces, it what keeps the molecule together. There are different kinds. Remember that all of the molecules have some forces in them, right? Because electrons are going around, so they will have something. So it says the energy required to separate molecules is less than that to separate a chemical bond. So intramolecular forces, so bonds have a greater energy than intermolecular. And we know that, right? We can easily separate a molecule, for example, salt. We can easily separate it when we put it in water, right? But it's not as easy to break up the chemical bond that keeps them together. In intermolecular forces, there's some attraction and repulsion forces that reach an equilibrium point, right? So that equilibrium point is the actual distance that they're at. And this is what we have been talking about. The intramolecular force, it's a weak force because we can do stuff to separate them. But the intramolecular, it's very strong. So this is my chemical bond. So this is my chemical bond that it's not as easy to break up as an intermolecular force. Depending on the type of characteristics of a compound, we can talk about its properties. But some of their properties cannot be explained only by the chemical bond that they have. For example, we have water. So water has a polar covalent bond. But even as a polar covalent bond, water should not be liquid. Water should be in a gas state. But because of the intermolecular forces between waters and waters, we have water that it is in a liquid state. So besides the polar covalent bond that the water molecule has inside, we actually need to talk about this intermolecular force that keeps the water together, right? We're not talking just about one molecule. We're talking about a glass of water, an ocean, a lake, etc. These are the types of intermolecular forces, the ones that we're going to see. We have 5. The first one is dispersion force or London force. It's the same thing. Then we have an ion-induced dipole. Then we have a dipole, we have a hydrogen bond, and an ion dipole. Very important, we have some van der Waals. Van der Waals forces are from, not the hydrogen bond, but it considers this bonds right here. It considers dispersion, ion-induced, and dipole. So van der Waals goes from here to here. Okay, so here we have the energy that they have to keep it together and the description of what that force is. So a dispersion force has an energy of 0.05240 kilojoules per mole. Then as we go down, we see that the energy is much greater, right? And again, this is a continuum. So we do not have this energy set in stone. Here you have the description, but we're going to see it as we go forward about what each of them include. Very important, and I should have written in larger. Intermolecular forces are accumulative, right? So if something has a hydrogen bond, it means that it already has dispersion and dipole, for example. We count the force that they're together by adding up all of the intermolecular forces that they have. The first force is going to be a dispersion or London force. It is present in all of the molecules. So regardless of what it is present. So it is the first force that keeps everything together. This force is the result of the fluctuation of the distribution of electrons in the molecule. Remember that electrons are always moving around. So for example, this helium atom has the electrons that are moving around. This other helium atom has the electrons moving around. So there's going to come a time where those electrons are in such a place that they can do a dipole. So for example, remember that electrons, their movement is just a probability of where they are. So for example, if I have my electrons, both of them here at this time, my electrons are going to be here, so the negative charge is going to be here, right? And at this moment, this immediate moment, I won't have any electrons here. So because this is positive, this is going to attract the electrons of the other atom to this side too. So in that case, we have an induced dipole. Because of that instantaneous moment, of that very, very small moment, my electrons are going to be in one side of my atom. So the other one, it's going to push the electrons to me. Remember, it's positive that attracts negative, right? And this dipole, and this positive, it's going to attract the other electrons, and we're going to have an induced dipole on atom B. So this is the dispersion force. How large is this force? It depends on the size of the atom and the electron cloud, because more electrons to one side, it's going to be a more negative part, and their molecular shape. We already talked a little bit about how important the molecular shape is to see where those electrons or electrons pairs. In this ion-induced dipole, for this type of force, we need to have an ion, of course, right? So we need to have an ion, for example, in solution. We need to have an ion that, with its positive or negative charge, pulls the electrons to it or to the other side. So in this case, it is pushing the electrons over to this side. It is a weak attraction, and that results when the approach of an ion induces a dipole in an atom or a nonpolar molecule. Because again, we have a positive charge, so it's actually this positive charge, it's moving the electrons depending on the charge that it has on the solution, right? For this one, we need an ion and we need a nonpolar molecule. Nonpolar molecules, remember, that have their ions equally shared, their electrons equally shared, they're going around. But because of this force, this positive force, I am forcing my electrons to spend more time on this side than on the other side. Then we have a dipole-dipole. The first force that we saw, the London forces, was an instantaneous dipole, right? It was an instantaneous dipole that was just the movement, the natural movement of the electrons, but we did not have a fixed dipole. We had an instantaneous, a very small moment in time. But in this case, the dipole is found in polar molecules. Remember that polar molecules have their electrons unequally shared. So, for example, here we have a hydrogen and a chlorine molecule. Chlorine is more electronegative. So the electron that the hydrogen is bringing into the chemical bond, it's going to spend more time on the chlorine than on the hydrogen, because the electronegativity is telling you that the chlorine likes to keep the electron to itself. That's why here we have an uneven sharing of electrons. So here we have a dipole that is there always. We always have a negative side and we always have a positive side because the electron spends more time here than here. Okay, so for the dipole-dipole, it's two dipoles, so it's two molecules that are polar that will keep attracting the electrons, right? So here it's attracting the positive side to the negative part. For this one, this negative part will attract the positive part and do a force. And it's exactly the same. So I attract another positive part. So this is negative, this is positive, this is negative. And in that way, I have an attraction because of the positive and the negatives. This attraction is called a dipole-dipole force. Another one that it's super interesting and it explains a lot of things in chemical compounds is hydrogen bonds. Hydrogen bonds are found in polar molecules that have hydrogen, it has to be hydrogen, directly bonded to small electronegative atoms. So we find hydrogen in HF, in HN, and in HO. So in this cases, this type of bonds will be hydrogen bonds, right? It is a super dipole-dipole because of the electronegativity between them. It makes the molecule partially charged, and since they are small, the molecules can get super close. So for example, if you see, here we are comparing molecules that have a hydrogen bond to those that don't have it, right? So for example, we're comparing CH4, which is methane. Methane is a gas at room temperature. If you see, my room temperature is around here, right? So methane is a gas. My water is a liquid. The boiling point of water is all the way to 100 degrees Celsius. What does it mean? That I need a lot of energy. So a lot of energy to reach 100 degrees Celsius. And for example, in methane, the boiling point was at maybe minus 180 approximately. So it doesn't need any energy to break up the bonds between methane and methane because it doesn't have hydrogen bonds. It only has dispersion bonds. So here we can see how water forms these bonds. Remember, water is a polar molecule, so water is polar. It has a hydrogen bond because it's a bond between hydrogen and oxygen. And we can see because a polar means a permanent dipole, right? So let's look at what it forms. Oxygen, it's the most electronegative. So it has the negative part. Hydrogen has the positive part. This is hydrogen, this is oxygen. So this positive part will try to bond with my oxygen. This negative part will try to bond with my hydrogen. This positive will try to bond with my oxygen. And in this case, we make a web of forces. So that web of forces need a lot of energy to break this one, to break this one, to break this one. That's why water has such high boiling point because of all the energy that we need to break those bonds. For the last one, and we also need an ion. For this one, it's called ion dipole forces. It occurs when we have an ionic compound mixing with a polar compound. It is very important when we're forming solutions. Remember that ionic compounds break completely up. So ionic compounds dissociate 100%. So 100% dissociated in solution. So remember that we do not find NaCl. For example, our example, it's NaCl. we won't find complete units. We will find them as ions. So this is what this drawing is letting you know. So sodium will dissociate as an ion. And for this sodium, if you see, sodium is positively charged. So it is attracting the negative part of water. So it is attracting the oxygen towards itself because of the positive negative forces. On the other side, chlorine, which has a negative charge, it is attracting the positive side. So it's attracting the hydrogens to itself because of the difference in positive and negative. So in that way, when we put salt into a solution, we completely break it up, and my water molecule starts surrounding them. That's why they mix up very good in solution. This is just a chart of how strong are these forces. We have intramolecular forces, which are chemical bonds, and we have intermolecular forces. So even if, for example, my hydrogen bond is super strong, it is not as strong as covalent or ionic bonds. So we go from dispersion to dipole-dipole to ion-dipole to hydrogen bonding, and we start accumulating force. So we accumulate force as we start adding up more forces. So for example, water will have dispersion because everybody has dispersion, dipole-dipole because it's a polar molecule, and hydrogen bonding. So we add all these forces up, and that can explain why water has a boiling point of 100 degrees C. Not as strong as the covalent bond that one molecule of water has, right? So here we're talking about many molecules, and here we're talking about just one molecule. So what makes one molecule stick together, right? And this we're talking about many. So this is it. If you have any question, just post it in